In this lecture, I want to focus on the chemistry of carbon. That's the most versatile and fascinating of all the chemical elements. This versatility follows from the great principle of carbon chemistry, that carbon forms strong covalent bonds with itself and many other elements. The main objective of this lecture is to explore the absolutely astonishing diversity of chemical compounds that result when you begin with element 6, the element carbon. I'm going to begin by focusing on the simplest compounds called hydrocarbons, with just carbon and hydrogen. Then we'll add other key elements one by one: oxygen, nitrogen, sulfur, and so forth. I'll also be introducing two fascinating kinds of interatomic forces called van der Waals interactions and hydrogen bonding, both of which play key roles in many carbon-based materials. But before we get started, I have to, in all fairness, offer you a kind of warning. Carbon chemistry, which is also known as the field of organic chemistry, it has a really bad reputation. It's safe to say that organic chemistry strikes fear in the hearts of science undergraduates and causes many otherwise confident scientists to roll their eyes and shake their heads. You see, carbon chemistry is exceedingly rich and varied. There are literally millions of different carbon compounds, and so there are literally millions of different chemical names of organic compounds. There are countless names of organic chemicals like alpha-ketogluteric acid and things like 1,3-dimethyl-2,5-diethyl-oxyphenol. These are the epitome of big, obscure science words. Other simple names like lysine or citrate, they're simpler to say, but have no real systematic basis in their naming. So a typical organic chemistry course may involve memorizing many hundreds of these names, maybe even thousands of names. You just can't get away from it. See, scientists have to communicate, and they have to do it with words and formula. That's the downside of organic chemistry. The upside is that the richness of carbon chemistry elevates the discipline from a methodical science to really an art form. The most skilled organic chemists are like great sculptors. They imagine the most incredible three-dimensional objects, and then they build them atom by atom. Only in this case, these atomic scale sculptures provide food, they provide your clothing, they provide shelter for the world. They relieve pain, they cure disease. Many of these organic chemists are quite literally the unsung heroes of our modern age. Like any art form, you can't appreciate the richness and beauty of these creations until you've learned some of the basic language, the rules of grammar, the conventions of the art form. And I have to emphasize that you wouldn't be listening to this lecture today. Your life would be inconceivably different were it not for the art and the science of organic chemistry. And that's what this lecture is all about. This lecture is in three parts. First, we're going to look in detail at carbon, that's element number 6, and its unique bonding strategy. That's to share 4 electrons with up to 4 different adjacent atoms. And those other atoms might include other carbon atoms. Understanding why carbon forms chemical bonds the way it does is the key to understanding why organic chemistry is so rich. Then we're going to use that strategy to assemble a variety of carbon-based compounds. And I apologize in advance for using lots of new chemical terms. I've tried to focus primarily on chemicals that I know you've heard of: alcohols, carbon dioxide, natural gas, things like that. But you may find that it helps to follow along with the guide to organic molecules in the course booklet that accompanies these tapes. And finally, I'm going to introduce 2 kinds of intermolecular forces. These attractive forces are called van der Waals attraction and hydrogen bonding. These forces help to hold together many organic substances. Okay, let's begin by thinking about the strategy that carbon has to adopt in its quest for chemical stability. Recall from the last lecture that chemical bonds reflect the tendency of atoms to attain a filled outer shell of electrons. That's with 2 or 10 or 18, 36, 54, and 86. Those are the magic numbers of electrons. And those numbers are rather mysterious, but they dictate the behavior of atoms in combination. These numbers also control the appearance of the periodic table of elements. In ionic bonds, electrons are transferred from one atom to another. This transfer creates positive and negative charges called ions, and these ions bond to each other by electrostatic attraction to form, for example, salt. And you have metallic bonds. In metallic bonds, outer electrons become delocalized, and they form a negative sea of electric charge, which isn't associated with any individual atom. So positive atom centers are bonded together within this electron sea like marbles and molasses. And then we had covalent bonds. In covalent bonds, 2 or more electrons from the outer atomic shells are shared amongst a few close atoms to form a molecule. Molecules such as N2 and O2 in the atmosphere, or H2O and CO2 in liquids. These are tiny, tightly bonded, electrically neutral objects. Now, each of these 3 strategies, to accept electrons or to give away electrons or to share electrons, can result in lower energy states and thus in effective chemical bonds. Now, there are only 3 major types of chemical bonds, and there are only a few dozen types of common elements, but there's an endless variety of chemical compounds. That's because the 100 or so elements of the periodic table can combine in lots of different ways. The element carbon has an unparalleled ability to form covalent bonds with 4 different neighbors. That includes strong bonds with other carbon atoms. And this ability means that you can devise ever larger and more complex structures just by adding more carbon atoms. It's sort of like playing with an infinite Lego or Tinker Toy set. In fact, more than 90% of all the chemical compounds that are known, they contain carbon. And the study of carbon chemistry, that is organic chemistry, is far and away the major focus of modern chemical research. I have to emphasize, this is an incredible economic enterprise. The total production of organic chemicals, that is, the production of plastics and paints and papers and glues, there's drugs, there's cosmetics, rubber, food additive, pesticides, all the cleaners and soaps you use, waxes, all the fuels you use, that's well over $1 trillion annually in organic chemistry. Now, the geometry of carbon bonding is governed by the 6th element's need for 4 additional electrons. They're provided by up to 4 surrounding atoms. Look at the periodic table here. Look at the position of carbon on the periodic table. It has a half-filled second electron shell. This special position of carbon, element 6, is the key to organic chemistry. You can quite literally think of organic chemistry as a game in which every carbon atom has to find 4 electrons from some combination of other atoms, and in the process satisfy the electron needs of all those other atoms. In concept, then, the rules of this game aren't very complex. As in all organic chemistry courses, I'm going to start by considering the varied compounds of carbon and hydrogen, what are called the hydrocarbons. That's the simplest part. Hydrocarbons are all around us, from simple gaseous fuels like natural gas and butane, to the liquids that make up most of gasoline, and also to solids like candles and the waxes that we use. We begin with a single carbon atom. That carbon atom needs 4 more electrons to reach its most stable configuration of 10 total electrons. So along come 4 hydrogen atoms. And each of those atoms needs 1 extra electron to reach their stable number of 2. So recall what we did. In this series of images that we saw from the last lecture, we start with 5 separate atoms. And then we see the electrons move. 4 hydrogen atoms surround the carbon atom, and the carbon is happy because it's found 4 extra electrons. The 4 hydrogen atoms are happy because each one gets to share one of carbon's electrons. And the result is methane, that's CH4, which is the simplest hydrocarbon. And in real life, this is what the molecule looks like in 3 dimensions. Now, you know methane as natural gas. It's what you pay for in your gas bill. It's a rich source of energy. By the way, pure methane is both colorless and odorless. What the gas company does is add a trace of a chemical that smells bad so you know if there's a problem with a gas leak. A key reason for the variety of carbon chemistry lies in the fact that it can easily bond to itself. That's an amazing ability. 2 carbon atoms can share electrons and thus bond strongly with each other. And you can represent such a covalent bond as 2 letters C with a single dash between them. That single line represents 2 electrons that are shared. And once you have that carbon-carbon arrangement, you can add hydrogens all around, 3 for each carbon to complete the picture. And so what you end up with is C2H6. That's this molecule, the chemical ethane. And you can play this game almost forever by replacing hydrogen after hydrogen atom with a group of 4 atoms, CH3, which is called a methyl group. And so here you see a methane molecule, and you add CH3 and you get ethane, and you add another CH3 and it becomes propane, and another one it becomes butane, and so forth. By the way, here's a curious fact. If you keep on substituting carbon for every hydrogen in this process, countless of trillions and trillions of times, you can eventually wind up with diamond. You see, in diamond, which is pure carbon, every carbon atom is surrounded by 4 other carbon atoms. And the result is this incredibly strong 3-dimensional framework where every carbon is linked to 4 others in a kind of trestle-like arrangement. Okay, so back to the hydrocarbons. You go from methane with 1 carbon to ethane with 2 to propane with 3 and so forth, just by taking away hydrogen atoms one at a time and replacing them with CH3 groups. Normal alkanes, that includes all the covalently bonded compounds with long, straight carbon-carbon chains. A backbone that's straight, surrounded by hydrogen atoms. And you use these all the time. There's propane, which is a common fuel. There's butane, which is a fluid, which is in common butane lighters. So when you have a butane fuel, you can see that liquid, and that provides you with the fuel. And you can conceive of almost any length chain. Candle wax contains normal alkanes with about 20 carbon atoms. And you can conceive of much longer alkanes. Although if you have more than a few dozen carbon atoms, the substances are just black tar-like materials, not of much use. And let's remember the point here. Carbon has 6 electrons. It wants 10 electrons. It's going to do whatever it has to do to achieve that number. That's the game we're playing here. The plot thickens when the addition of carbon branches. That is, carbon in a long chain bonds to 2 other carbon atoms, but can also bond to a 3rd atom in kind of a T-like arrangement, or even a 4th carbon. Look at this. This simplest branched hydrocarbon is isobutane, with a T-shaped arrangement of 4 carbon atoms. And then you add hydrogen atoms all around. This T-shaped molecule differs from normal butane, but it has the exact same formula, C4H10. Now here are normal butane and isobutane. This is what organic chemists call isomers of C4H10. 2 isomers are molecules that have the exact same combination of atoms, but they're arranged in a different configuration. And as the number of carbon atoms increases one by one, the number of isomers increases exponentially. So when you go to pentane with 5 carbons, there are 3 different isomers. You have the normal alkane, and then you have a branched alkane, and then the cross-shaped version. By the way, I'm not showing all the hydrogen atoms. It just gets too crowded on the diagram. It turns out that hexane with 6 carbon atoms has a total of 6 isomers. And try to sketch these out at home sort of as an exercise. Okay, then we come to octane. Octane with 8 carbon atoms is of special interest to those of us who drive. Octane has 18 isomers. And one of these isomers, called isooctane, has a backbone of 5 carbons and 3 branching carbons. Look at this. This isomer turns out to be particularly effective at stopping knocking in your car's engine. By contrast, normal heptane with 7 carbon atoms in a row is particularly bad in this regard. The octane rating of gasoline is a scale that goes from 0 for pure heptane to 100 for pure isooctane. Now life gets much more complicated when you get to carbon compounds with a dozen or more carbon atoms. Alkanes with 20 or more carbon atoms have literally thousands of isomers. It turns out that many of those compounds feature 1 or more carbon rings. And this is a new and fascinating wrinkle. Ring-like compounds of carbon and hydrogen are called cyclic hydrocarbons. Here's a molecule called cyclohexane. Again, think about the bonding needs of each atom in this molecule. Every carbon atom has 2 of its 4 covalent bonds satisfied by other carbon atoms, and the other 2 covalent bonds satisfied by hydrogen atoms. The result is a compound with a composition C6H12. Each hydrogen gets to share an electron with carbon. And as you can see here, ring hydrocarbons can also have branches or additional rings, nested together or separated by chains in almost any imaginable arrangement. Try drawing different combinations yourself. The only rule is that each carbon must have 4 neighbors, either carbon or hydrogen. Okay, now that's just the tip of the hydrocarbon iceberg. As if all that weren't complicated enough, carbon has another trick up its sleeve. It can also form a double bond with itself. That means that 2 of the 4 electrons required by each carbon is shared. This kind of double bond is usually drawn with 2 C's with a double line or an equal sign between them. And that double line represents 2 pairs of shared electrons. That tells you that each carbon atom has 2 of its 4 missing electrons taken care of. The other 2 can be satisfied by hydrogen atoms or other atoms. Double bonds have a different character. They're more rigid. They have more energy. And the simplest of these double bonded hydrocarbons is ethene, shown here. This is a member of the alkene series, C2H4. All the variations that apply to alkanes, all the chains, the branches, the rings, are also found in alkenes. The formulas differ from alkanes because for each carbon-carbon double bond, there are 2 fewer hydrogen atoms. As before, normal alkenes are straight, so we have ethene and propene and butene and so forth. A compound of special interest is the ring molecule C6H6, which has 3 carbon-carbon double bonds. That's called benzene. That's another one of these special names. Now, here's a picture of benzene. It used to be used commonly as an industrial solvent and a cleaning agent, but now it's known to be somewhat carcinogenic, and so it's much less widely used. In this beautiful 6-carbon ring, electrons are shared around the ring, which averages 3 double bonds and 3 single carbon-carbon bonds. And here we come to a curious feature. Because the distribution of electrons isn't fixed, in fact, the 3 pairs of shared electrons resonate. They constantly switch around and around that ring. Now, carbon also occasionally forms a triple bond with itself. And you guessed it, this situation is drawn as 2 C's with 3 short lines between them. That means that 3 pairs of electrons, 6 electrons in all, are shared between 2 carbon atoms. In this case, each carbon atom is 3/4 satisfied and needs only 1 more hydrogen atom. So hydrocarbons with CC triple bonds are called alkynes, and here's the simplest of those. It's ethine, or more commonly known as the welding fuel acetylene, C2H2. Actually, acetylene and ethene, they're the same names, and it would be more logical to call this ethene, but that's the nature of organic chemistry. There are many common names that defy the more orderly conventions of the nomenclature. Again, all the rich variety of normal and branched and ring complex that you see in alkanes and alkenes are also seen in alkynes. The reason society values hydrocarbons so much is because of their unique and valuable properties. As with all chemicals, the properties of hydrocarbons are closely related to their structures. All hydrocarbons burn. They combine with oxygen to produce heat, plus water and carbon dioxide. The smallest molecules that have 4 or fewer carbon atoms are typically gases or very volatile liquids. That includes propane and butane. These are common fuels that are easily purified and easily transported. Then there are larger straight-chain molecules. They're more massive and thus have progressively higher and higher melting and boiling points. I want to remind you of this by the behavior of a candle. When you light a candle, recall the process that's going on. You have 3 different states of matter coexisting. You have solids, liquids, and gases. And that's because as you change the temperatures, you raise the temperature, the solid candle wax first melts, then it becomes a gas. Candle wax is a hydrocarbon with about 20 carbon atoms, typically a straight chain hydrocarbon. It turns out that branching and cyclic hydrocarbons usually have lower melting and boiling temperatures than the straight isomers. And that's because these molecules, you can think of them as being lumpy. They don't pack together as efficiently in a solid form. So long straight molecules pack together sort of like uncooked spaghetti in a box, that's very dense. But if you have branched or ring molecules, they pack less efficiently. That's sort of like macaroni in a box. And so you have less opportunity to form an orderly structure and have the bonds forming next to each other. Okay, hydrocarbons are by far the easiest part of carbon chemistry. The chemistry of carbon very quickly becomes complicated as additional elements come into play. Oxygen, that's element 8, is a vital element in the vast majority of organic compounds, including almost all the molecules in your body. Oxygen needs 2 extra electrons. It has 8, it wants 10, so it often forms a double bond with carbon. And that's a letter C next to a letter O with an equal sign between. That equal sign represents 2 pairs of shared electrons. The oxygen atom in this case is fully satisfied. The carbon atom has 2 of its 4 extra electrons and it needs 2 more. And so you can see this behavior displayed, for example, in carbon dioxide. Each carbon atom has 2 neighbors, with each oxygen atom sharing a pair of electrons. That's the simplest carbon-oxygen compound known. And then you can vary this. Here's a very simple organic compound with oxygen. It's called formaldehyde. Actually, this has 1 carbon atom, and it could be called methaldehyde, methane, ethane, so forth, but that's not its common name. You may have heard of this chemical, formaldehyde. It's used to preserve lots of biological specimens. The formula is CH2O. The carbon atom has 3 neighbors. The oxygen atom shares a pair of electrons, and 2 hydrogen atoms complete that picture. And there are other larger aldehydes. They also have that CO double bond, and they're formed by replacing one of the hydrogen atoms in formaldehyde with a methyl group, a CH3, just as we did before, to form longer and longer compounds. Now, oxygen atoms can also form part of a chain or a ring of atoms. Oxygen can bond to 2 carbon atoms. In this case, also, the oxygen is fully satisfied while the adjacent carbon atoms need 3 more electrons. Remember, the rules of the game are always the same, but like any interesting game, there are lots of different strategies. Let's look at a different important group of atoms. This is the OH or hydroxyl group. So if a hydrogen atom bonds to an oxygen, that hydrogen atom is happy. It has its 2 electrons. But the oxygen atom needs 1 more electron. So the OH group thus forms a single bond with carbon. And that single bond can, for example, replace a hydrogen. So if you start with methane, CH4, and substitute an OH for a hydrogen, you get methanol. Methanol is the simplest of a huge group of molecules called alcohols, all of which have a COH linkage of atoms at one end. Methanol is also known as wood alcohol. It's poisonous. It should never be consumed. Longer alcohols, including this very popular molecule ethanol, are formed by substituting carbon atoms for a hydrogen atom. So you get a whole series: methanol, ethanol, propanol, butanol. It's really like learning the whole new language. You put OL on the end instead of the E for methane, ethane, propane, and so forth. Okay, now it gets even more interesting. You can start with methane and replace 1 hydrogen atom with OH as an alcohol and 2 more hydrogen atoms with an oxygen. And these form the aldehydes. And then you end up with formic acid. Formic acid is the simplest of what's called the carboxylic acids, which play key roles in energy-producing chemistry of living things, metabolism. Again, there are literally thousands of carboxylic acids. And you can have 2 or 3 or more of these carboxyl groups to form the dicarboxylic acids and the tricarboxylic acids and so on. Remember, we've introduced rules that can produce countless organic compounds. And so far, we've only talked about 3 elements: carbon, hydrogen, oxygen. I don't know, maybe you're like me, you'd like to take a deep breath before we introduce one more. That's nitrogen, element 7. Nitrogen needs 3 extra electrons. And here we add lots of different strategies. By the way, I do think of this kind of chemistry as a game. With carbon, hydrogen, and oxygen, it's a pretty simple business. It's sort of like checkers. But as you add all these other elements, nitrogen and sulfur and phosphorus, organic chemistry begins to look a lot more like chess, with lots of different pieces that can make different moves. So you have all these different strategies in building up organic molecules. So think about nitrogen. A single nitrogen atom can form a triple bond with carbon, as in hydrogen cyanide. That's HCN. But hydrogen can also attach to carbon atom as an NH, or an amide group. That has a double bond, or it often appears as part of an NH2 group, an amine group, with a single bond to carbon, as we're going to see when we talk about the amino acids. Nitrogen can also substitute in a whole variety of ways, in chains, in rings, in branches. Try this yourself. Remember that nitrogen needs 3 electrons and carbon needs 4. So I want you to imagine how nitrogen might substitute into a 6-carbon ring like cyclohexane. In living things, sulfur and phosphorus add even more complexity to these amazingly diverse structures. Let's look at the periodic table. Sulfur is element 16, right below oxygen. And it often bonds in a way that's very similar to oxygen in organic compounds. One important difference is that most organic sulfur compounds have the awfulest smell you can imagine. And then there's phosphorus. That's element 15. It's right below nitrogen in the periodic table, and it shares some similarities with nitrogen chemistry in organic molecules. We're going to learn more about some of these phosphorus compounds in lectures on molecules of life. But the bottom line is the same. Each carbon atom wants 4 more electrons, and that requirement guides virtually all of organic chemistry. For the remainder of this lecture, I need to change gears and switch our attention to 2 kinds of molecular bonding. All the complex molecules described so far are compact. They're electrically neutral objects. They range from 3 atoms to thousands and thousands of atoms. So you have CO2, you have CH4, and so forth. All the bonds within these molecules are covalent. The electrons are shared between 2 or more atoms. The molecules themselves are electrically neutral. But think about that. If these molecules are electrically neutral, how can they possibly form solids like candle wax? This is a solid material. It turns out the answer lies in 2 kinds of intermolecular forces called van der Waals attraction and hydrogen bonding. You see, all molecules are surrounded by electrons. And when 2 molecules approach each other, every electron and every proton in one molecule experiences an electrostatic force from every electron and every proton in the other molecule. Remember Coulomb's law of electrostatic force. Any 2 charged objects anywhere exert a force on each other. So when the 2 molecules get close, the electrons in both molecules shift positions slightly as a result of these forces. The molecules are still electrically neutral, but they develop regions of slightly more positive and slightly more negative charge. And this deformation of electrons can cause a small attractive force between the molecules. That's what's called the van der Waals attraction. There are a lot of common layer minerals, including talc, that's baby powder that you use, and many varieties of clay, and also graphite in your pencil. They're held together by van der Waals attractions between layers of atoms, and the layers themselves are electrically neutral. Here's a model of the graphite structure. It's carbon bonded to carbon. But if you look at it in just the right way, you see the layers of carbon atoms extended like two-dimensional molecules, and those layers, they have no net charge. As a result, materials like graphite feel greasy because you're breaking weak van der Waals forces with your fingers. The molecules just slide over each other. You feel the same kind of greasy effect with candle wax and soap, both of which are held together with van der Waals attraction. The other type of intermolecular force is called the hydrogen bond. But before I explain that bond, I've got to tell you about a class of compounds that relies heavily on hydrogen bonds. So far, all the organic molecules discussed here have been relatively small, with at most a few dozen atoms. But one of the greatest impacts of organic molecules in everyday life has come with the widespread introduction of much, much larger molecules called polymers. Polymers include synthetic fibers like nylon and rayon. They include most of the paints and glues you use day to day. They include foam insulation and all the many kinds of plastic. Also lots of fibrous biological materials, including spider webs and also clotted blood. Those are polymers. Now, many polymers begin as liquid solutions of monomers, which are just small carbon-based molecules. The monomers of nylon, for example, there are two similar 6-carbon chain molecules. When these liquid chemicals are mixed, though, you get strong, flexible fibers, and they can be pulled from the solution. So you have a liquid, and you actually can pull a fiber right out of that liquid. Some polymers, including spider webs and hair and synthetic fibers, are formed from simple chains of molecules like amino acids, which I'll talk about in a few lectures. Now, plastics form from complexly intertwined polymer strands, and the hardness and the flexibility of a polymer depends to a great extent on the cross-linking between these strands. See, covalent cross bonds may form if the original monomers are branched, but the other important kind of cross-linking, and the one that we're talking about here, is hydrogen bonding. Hydrogen bonding is critical to the formation of polymers. Electrons are never uniformly distributed over an entire molecule, and we saw how this behavior could affect van der Waals attractions. In fact, a hydrogen atom on the outside of any organic molecule often develops a slight positive charge. And other atoms, like oxygen, it often has a slight negative local charge. So hydrogen bonds form from the attraction between the slightly positive hydrogen on the one hand and exposed positive atoms to other negative atoms like oxygen. Each of these individual hydrogen bonds is relatively weak, but plastic-forming molecules can contain an abundance of hydrogen, and thus polymers typically have numerous hydrogen bonds that hold them together. I want to look at another example. Let's look at the case of water. Here's a picture of a water molecule. This is a slightly bent molecule, and the hydrogen side is slightly positive because hydrogen gives up an electron, and the oxygen side is slightly negative because oxygen takes the electron. And as a result, here's a picture of the ice structure, a small part of an ice structure. Now, any one hydrogen bond between hydrogen and oxygen isn't very strong, but the strength of numerous hydrogen bonds gives ice, that solid H2O, its hardness. You know that if you hit a piece of ice with a hammer, it shatters, almost like that ceramic coffee cup from the last lecture. Hydrogen bonds are directional, so ice is brittle. Well, in this lecture, we've seen that the chemistry of carbon is extraordinarily rich, and it's diverse. And it's diverse because of two factors. First, each carbon atom needs 4 extra electrons. And second, it can satisfy that need by bonding to another carbon atom or atoms of many other elements in a whole variety of ways. We saw the distinctive bonding strategies of hydrogen, which needs 1 extra electron. And there's oxygen or sulfur. They need 2 extra electrons. And nitrogen and phosphorus, which need 3 extra electrons. Literally millions of carbon-based chemicals play this game. These molecules then link together using van der Waals attractions and hydrogen bonding to provide most of the physical materials of our surroundings, and of ourselves, in fact. In the next lecture, we're going to continue our exploration of the material world by examining the states of matter, that is, the solids, the liquids, and the gases.